Hello everyone. I guess my screen is recording and I thought of making a video on convoluted neural networks as most of my friends often face difficulty in this topic. It's quite easy though. So let's begin. So what is a convoluted neural network? It's just a simple neural network but with a lot of steps. Not a lot, but typically 4 steps. Before going into that, we'll know what are convoluted neural networks used for. They are used for image processing. When you have an image, the machine doesn't know what kind of object the image holds. That's why we need to make the machine understand that it's the image of an object. What type of object? Is it an object? These types of questions we need to answer, and for that we use convoluted neural networks. So coming into what is an image, many of us know what is an image, but the structure of an image, typically an BMP, also called bitmap image. In this type of image it is an array of RGB values. So each pixel you see has some RGB value ranging from 0 to 255. They make up a pixel, and that pixel's color is displayed on the image. Suppose we have an image like this one. We can see and understand that it is an A, the letter A. But a machine doesn't know that this is an A. So how do we train it? To train the neural network to understand an image and say whether it is a 4 or A, some number, alphanumeric character, or whatever, we need to follow 4 steps. The first one being convolution layer. In this layer, what we do, we see the whole image and try to draw an outline like this. We try to draw an outline to help us understand what are the features of an image. Suppose from this image we can understand that this is the part we should be focusing on. This is the basic outline. Anything other than this is just garbage. We don't need that. This part is the main structure of the letter A. So we need to focus on this region. So with convolution layer, we do just that. We can use in convolution layer, we can use something called Sobel operator to figure out the edges. It works in this way. Suppose you have some RGB values XYZ dot 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 dot. So we take the average of this value stored in this. We took the average and place it. Suppose the average came out to be 13, 12 and 125. So we just do one thing, we put the values in the respective fields like 13, 12, 125 for each of these RGB values. Each of these has the value 13, 12, 125. This is the work of Sobel operator. This just creates an outline for your image to extract the features from the image. This was just one type of operator which can be used, that is Sobel operator. I'll link the code for this. It is written in C by myself, so I'll link that in the GitHub, or you can just visit my repo. Then comes the second layer where we apply the ReLU function or sigmoid function. So what are these functions? ReLU function is, suppose this is the graph for x and y axis. ReLU function, just for an image, suppose the red color is suppose 56. We don't want 56. We want it to represent either 0 or 1. That is, suppose if the red value is more than 155, we set the pixel's red value as 1, and if it's less than 155, we just switch it to 0. So we hard code that. That is, the function is straight like this, no, like this, straight. It's 0, the value is 0, 1. It's a step function. If it's greater than 155, we just switch it to 1, else we switch it to 0. Now what's sigmoid function? Sigmoid function tells us, no, why should we hard code them and use step functions? It can be something like this, fuck, like this, okay? It can be like this, like 0.5 here, 0.7, and like this. Any value it can be from 0 to 1 based on the condition. That is, if greater than 155, you should put it to 0.7. If greater than 150, you should be putting it to 0.6, and so on. So these functions are placed over the whole image. So what we do, suppose this was our image and these are the RGB values. So when we put the when we pass the image from this function, that is the ReLU or sigmoid function, here suppose it's 25, we'll set it to 0. The green value is 25, we'll set it to 0 because it's less than 155. Since it's less, we'll put it to 0. Blue is also less, so we'll put it to 0. And if it were, suppose 158, we would have put it to 111. That is, the grid will have the value 1. This will have 0. This will have 0. So on. This is the work of the ReLU or sigmoid function. Now comes the third part, that is the pooling layer. What we do in pooling is that we cannot see, the image is a very big grid. Suppose it's a 256 times 256 grid. So training this many nodes would be a pain. Pooling is taking the, just like the Sobel operator, taking the average of the area's values, taking the average of these values. Suppose we take the 4 or the 9, you can take the 9 also. You take these values and you put the average as a single grid, making this whole structure 1, 2 and 3. First we'll have this one. Suppose this comes out to be 1, then this comes out to be 0, then this comes out to be, suppose 1. So like this we shorten the image to get it to a structure like, suppose we get it to a structure which is a much smaller structure than the original image. Okay. So our A becomes, this is a very small, but it should be bigger than this. Like, we need to capture the features, otherwise it will be of no use. Suppose this was the function. This is our new image, and we can say this is the letter A. These grids. These grids. It's a much smaller image than this. This is a very big image. We turned it into a smaller image by pooling, taking the average of these grids and putting it as a part of here 1 0 1 and dot dot dot. So this was pooling. We get to a smaller image, which is a representation of the bigger image with exact same features. Okay, now after we get to a smaller variant, we can now introduce our multi-layer perceptron. Perceptron, as we know, is a neural networks. In neural networks, perceptrons are connections from a node to another node. This is a perceptron. Okay, so now coming into MLP, we'll use MLP now. We'll okay, so this image is just nodes. These are the nodes. Okay, these small grids, these are the nodes that we train on, and this image is represented in the form of matrix. 0 1 0 x y z some dot 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 other value, like this. This is the image where these are the pixel values. See, this is the representation of the letter A. You can see. Okay. So after we introduce MLP, these are just the nodes. Don't need to get scared from this diagram. This just looks a bit scary because of all the neural networks being interconnected. So this is the structure of the nodes. This is nothing but the grid, the pixel grid. It has the value, it has some RGB value, nothing else. All of these are the grids, that is flattened grid, flattened image, sorry. These are the flattened image. It's the array of the RGB values. The image is flattened. The flattened image looks somewhat like this: 0 0 1 1 0 0. These are the, after pooling, these are the pixel values we get. No, see this. From this is after pooling. After pooling, we get the grid as the matrix as 0 0 1 1 0 0 dot dot dot, and so on. The zeros following by 1 1 1 dot dot dot. This is the flattened image, and these are the nodes. The nodes in the MLP layer, these are the nodes. These. We now train the machine learning model. We know what is backpropagation now, so we train the machine learning model to identify the patterns where our activation function is getting targeted. Just like in this node, we can see from this, the third node has a value 1. See, first, second, third. The third node determines that yes, the color pixel, the value of the pixel is indeed 1. That is, the object's features match this function. So third is selected. Third's activation function is accepted. So in the fourth also we have a 1. So In this case, this will also have a 1. Okay, so like this it follows. All the pixel values which have 1 will match our image of A. There is a 1, so it will match this one. And so once they match, the activation function generates that okay, this one is correct, our machine is identifying it correctly. So what do? We proceed. It also identifies with this, it checks with this, it also checks with this and finds a match, and it's also generates an output. It checks the output if it's right or wrong. If it's a no, then we get a wrong output, so our model retrains itself. This time it goes to yes and we get the right output, so our activation function strengthens itself. That is how machine learning models train itself. It's typical machine learning after this process. Suppose this function was activated and this function also generated this. That means this one, so this is the activation function for this node. This one is the activation function for this node. It is not the activation function. This one gets activated due to this is a weight. The weight it carries is making this node to get activated, and this output is making this one to get activated, and so on. What does it mean to get activated, you may ask? So to get activated, what I mean, in what activation functions in general do is, I'll give a brief about it, as activation functions it needs another video. But activation functions are like this. Suppose you have suppose n numbers, and you need to find if the sum of them is greater than 10 or not. So what does the suppose this is the node, and this node sends an output. This node is this, and this one checks this activation function is this, f of sum if greater than 10, then proceed. This is the function, activation function for this. Suppose we get the sum from the previous node, that is this node. We get the sum. The sum is passed into this node, and this node checks if the sum is greater than 10. Suppose it is greater than 10 and the numbers were 9, 2 and 1. So it's 12, so it's greater than 10, so it's a yes, and the function is returning a yes, that is a true value, and so it goes to the next node, and this node checks if the value is yes or no. If it's a yes, then congratulations, your machine learning model is successfully predicting. If no, we just retrain the model to identify it correctly with some other value, some other weight. To understand more about this backpropagation step, I'll make a video on the ultimate algorithm for machine learning, that is the backpropagation. I'll make a video for that also. But basically this is what the activation function do. And since these two were already activated, we can see these two needed to be activated. Since it's a 1, they are passed on to the next nodes and eventually leading to a yes. And after successful attempts, suppose 10 no, we'll say 100 or 1,000 to 1,000 epochs, our machine learning model finally learns to identify the pattern in this image, and it will generalize a solution which will then identify any patterns from the A. Suppose this is our A, somebody's A might be this, their A might be this. It can generalize it using the machine learning algorithms. And this was our MLP, multi-layer perceptron. We also learned about activation function while in the process. And this is the final output, that is the prediction. After we pass the flattened image through our MLP that is trained, after training it, we get an output, yes or no, yes or no. And if it's predicting correctly, we know that our model is trained, and finally we can deploy our model. So this was it about convolution neural networks. Hope you like it. Thank you. Signing off.